Chapter 3 is a great chapter in this textbook that connects lots of different ideas about matrices through the ideas of matrix transformation. There's not a ton of MATLAB work to do because this chapter is so idea-driven rather than task-driven. So you definitely want to read this entire section very carefully. We're going to think about matrices as functions, and they're transforming a vector in one place and transforming it into another, just like a function takes an input x and transforms it into an output. All right, so in the case of a transformation where we have an input, right, and for any matrix, the vector input has to be in Rn. Why? Well, that's the number of columns. And when I do matrix multiplication, right, so I have a matrix A times a vector B, right? Well, the vector B has to have the same number of components as the columns of A, or I can't do the multiplication, right? So we know that the domain is always Rn, and the codomain, or the place where the vectors, right? I'm sorry, this should be an X, and the B's over here, sorry. So the vectors X have to be in Rn, and the vectors B, just by the definition of how we multiply vectors, have to be in Rm, whatever the number of rows is, rows in the matrix is. Each of these interactives that they have are important to take a look at, and I strongly suggest that when you read, you consider them carefully. What they do, however, is they go through one particular matrix transformation, and they describe what it's doing. So here we have the idea, right, that we have a matrix A times a vector, which has x, y, and z coordinates. So they're considering a vector like V, which has components in the x direction, the y direction, and the z direction. All right. And so we do this matrix multiplication, which is the matrix times the vector V, which has components x, y, and z. And notice that what happens when I do this, when you do this matrix multiplication, I multiply the top row by the vector v, and I just get an x, and I multiply the second row by the vector v, and I just get y, and then I have the last row is all zeros, so the final component of v is 0. So they're explaining, in some cases, we can just see what the matrix multiplication does. Geometrically, though, is interesting. What it's doing is it projects all of these points vertically onto the xy plane. Whatever their x coordinate is stays consistent. Whatever their y coordinate is stays the same, and their z coordinate goes to 0. So in 3D, this just drops everything vertically or pushes it up vertically until it's sitting in the xy plane. Now, it's interesting, they give several examples, and you should begin to understand that these are standard transformations that we should know their matrix to. So reflection matrix that reflects right over the y-axis, right? The reflection is through the y-axis, so everything on the right side of the y-axis ought to be able to look at itself in the mirror as if the y-axis was the mirror. And they go through a really nice example of a reflection. And by the way, we'd switch the minus sign from the top left down to the top right to reflect across the the x-axis, right? So the one they're showing switches across the x-axis, but we can reflect through the x-axis as well. And I don't know how well this is going to show up, but you can click on the vector heads and move them around and see where the reflection point is. And again, we're just reflecting through the y-axis. You should definitely take some time to play around with these interacts. They show a dilation, which is just a scaling. One of the reasons they call multiplying by a scalar, right, a scaling value. And so here, everything is going to be magnified 1.5 times, right? If the values along the main diagonal were, say, 1/2 and 1/2, then I would be scaling by 1/2. And I don't have to scale both the x and the y component the same. I can scale in the I can scale along the horizontal axis by, say, 2, and scale along the y-axis by a factor of 1/2, for example. So definitely, and they'll have an interact, definitely take a look at what the scaling factor of 1.5 is doing. And you can see the picture of the cute baby is larger, right? The baby is larger in the figure on the right after the transformation is applied. The identity transformation is the identity matrix. So the identity matrix has zeros everywhere but the main diagonal, and the main diagonal entries are all ones. And of course, the identity matrix will just leave the baby picture exactly the same as it was. We have a rotation matrix. So this is actually rotating by 90 degrees counterclockwise. And you can see these points. The way I knew it was 90 degrees was this point here on the negative y-axis gets mapped to the positive y-axis. So that's a 90 degree. That angle is a right angle. But all of these are getting mapped. Every point will just get mapped. The distance from the origin will stay the same, and it will just keep that same radius and move the point 90 degrees counterclockwise. Yes, that's counterclockwise. By the way, there is a standard way to define a rotation matrix where we use cosine theta in the top left and sine theta in the bottom left and minus sine theta in the top right and cosine theta. Anyway, so we'll show that matrix. I believe the book does, and if the book doesn't, I certainly have it in my companion notes on the MATLAB side. But we can use sines and cosines. We can put in any degree value or radian value for the angle that we want to rotate by, and then just calculate based on the sines and cosines. But just as we're talking about these, I will say that there are some basic ones that we tend to know. They're all zeros and ones with positives and negatives that will do 90 degrees, 270, 180, like all of the basic transformations of 90, 180, 270, 360. They're all nice looking matrices like this. And that's, of course, because the cosines and sines of 90, 270, 180, all of those are either 0 or positive or negative 1. So the matrices turn out to be nice. All right, then the final example they give is of a shear. Now this is interesting because this is the first time we've had, well, it's not the first time, but you'll notice that we have the identity matrix except for a value here in the top right. And this will shear in the x direction. And if I have a 0 up here and a non-zero value here, it will shear in the y direction. And you can see why they're showing that here. So definitely take a look at the shears, and that's a standard transformation. Now, definitely want to consider what it means by the domain and the codomain. And a lot of people get the codomain confused with the range. The range is a subspace of the codomain, right? So what do we know? We know the domain is Rn, the number of columns, right? And the range where the vectors that get transformed lives in Rm, but it may not be all of Rm, right? So this matrix maps from Rn to Rm, and the range will be in here, right? but it's not necessarily all of Rm. So Rm is called the codomain, the place where the vectors get mapped to, and then the range is whatever part of Rm that we're the actual vectors that we can find in Rm that do have a preimage, right? Some x in Rn. So the book gives a helpful function image, right? So here's the domain of Rn in Rn, and here's the codomain, right? But the range may only be a subset in the codomain. Finally, they talk about the matrix transformation. We get more of a function notation, right? So we have a transformation T, and we refer to it as T of x. Now remember, these x's are vectors, so the transformation is applied to a vector, and it maps from the domain Rn into some codomain Rm. And what these matrix transformations, they have a matrix that's associated with them. It's called the standard matrix. So this matrix is the standard matrix of the transformation T. And so every linear transformation has a standard matrix, and every matrix can be the standard matrix for some linear transformation. And Margalit sums this up here. Again, this is a huge content chapter. There is a section. There's a ton of information here. And this is just saying, hey, that we have this function that's going to be defined. This linear transformation is going to be defined by whatever this matrix multiplication is when I use the standard matrix, the associated matrix A. And it has, as we've said 100 times, the domain is in Rn, the codomain is Rm, and the range is in the column space, right? The range lives over here. And the range is the column space. What does that mean? Well, the column space is the subspace of Rm where I can actually find vectors y that get mapped from here, right? So if I have the vector x living in Rn and it gets mapped over into some vector y that lives in Rm, then this vector is said to have a preimage, which is called x, right? And if I can find a preimage for y, then it's in the column space. It's in the range, right? But not every vector y that lives in Rm is in the column space. As you know, sometimes the column space is all of Rm and sometimes it's not. That depends on how many pivots we have in our associated matrix. And in the final section of the chapter, they just make the point that any linear transformation has an associated matrix, and any matrix transformation is a linear transformation. Any matrix can be associated with a linear transformation. And they ask 4 questions. And they're saying, well, evaluate what happens to the vector u under the transformation T. Well, the answer is I just take the associated matrix and multiply it by u. That's a matrix operation. Can answer that question. And the same is true for the other questions they ask. They're saying, hey, what if I have the vector b that lives in the codomain? Find a vector v such that the transformation T sends it to b. Well, now I'm solving the matrix equation AV, A times the vector V equals B. So I'm trying to solve this. Well, I row reduce the augmented matrix where I augment A with this vector B. And I can row reduce that. And so again, this question number 2 about the transformation is just asking questions about matrix operations. Question number 3, does there exist a vector W, that's the preimage, excuse me. They're asking if there is some vector W in R3, I'm sorry, that's the codomain, such that there is more than one V in R squared with TV equal to W. Well, again, this is asking whether there's more than one solution to that equation that I just had here, right? We're asking not just if there's exactly one solution to A times the vector V equals the vector B. The question now, I'm sorry, they did W, right? So A times the vector V equals the vector W. They're asking, is there more than one, right? And then this final question, find a vector which is not in the range of t. Well, here we're looking for a place where I choose W in a way that we have an inconsistent matrix to row reduce. So each of these, all of these questions, as they're saying, translate into questions about the corresponding matrix A, the standard matrix for the transformation. So this is a content-rich section, and they've got great interacts. So I strongly suggest you spend several minutes reading through the content. Even though I've gone over it very quickly, I've just given an overview, and it would be really good to read this at least once and maybe a couple of times, and definitely spend some time on the interacts to help understand what's going on with these linear transformations and their standard matrices.